Get started. Hello again, everyone, and thank you for joining Mauser Analog Devices and Würth Electronic for today's webinar, Battery Management Solutions for Energy Storage Applications. My name is Mark Patrick, and I'm the Director of Technical Content for Mauser Electronics here in EMEA. And joining me today are Nigel Brook, Senior Product Manager for Energy Storage Systems at Analog Devices, Martin Leihensieder, Technical Lead for Signals and Communication at Würth Electronic. For those of you who might not know Mauser, we are a global distributor of the newest semiconductors, passives and connectors from over 1,100 manufacturers. We stock over 69,000 products from Analog Devices and over 19,000 from Würth Electronic. So if you're inspired by today's webinar and want to investigate their battery management solutions further, we have whatever components you're going to need in stock. So just a couple of housekeeping items to mention. Please ask any questions you may have on the presentation using the Q&A button below. And we will answer as many as we can, both during the presentation if it's applicable, or certainly at the end of the presentation when we will have a specific Q&A session. If you have any technical questions around audio or webinar function, then please use the chat function and someone from the Mauser team will help you as soon as possible. So with that, let me hand over to Nigel, who's going to kick the webinar off.
Wonderful. Hello, everybody, and thank you very much for attending the webinar today. So what we're just going to cover today is our battery management solutions around energy storage and how this works with isolation and Würth electronics as well. So I shall just give a brief introduction. So just at a top level, this is kind of the way that Analog Devices is trying to enable the energy transition. We look at this as kind of three separate sort of problems, and we're going to talk about storage today, but we have business units that cover conversion, so your solar, wind generation, generating the electricity, how you manage the electricity once you've generated it, and how you store in both grid and residential applications. So today's webinar will concentrate on the energy storage part of the transition, and we'll focus on residential and grid storage. So just at a top level, why is battery storage becoming more important? Now, some of these are obvious, some of the applications are obvious, some of them are kind of new emerging applications in the industry. So, when you drive down the motorway and you see a wind farm or a solar farm, and you'll see the big shipping containers sitting next to them, those are that's an area of energy storage around grid and power plants, which we call grid utility sort of space. We also have areas in industrial that can be used for saving power in industrial buildings, and also for use for EV charging infrastructure, and areas for energy storage in residential as well. And an increasing area that's coming up is also grid stabilization on the grid, where we're looking at doing local microgrids and stuff and energy storage around that. So there's actually lots of different applications for energy storage. There would still need to be energy storage even without the whole energy transition, but there's lots of different places where energy storage is used in the grid. Just to give you kind of an overview of the sort of technologies that Analog Devices sells into the energy storage technologies. So we sell a lot of our cell monitors, and we'll concentrate on that a lot today. We also do pack monitors for measuring current and stuff on current and voltage on the top of the pack, and ISO SPI, which we work together with Würth to generate solutions for isolated communications up and down the chain of the battery monitors and cell monitors. But there's also a lot of other components around these systems that are needed to make a battery rack or an energy storage system. So we have also a lot of other things in communications, isolations, precision, power management, microprocessors, cybersecurity, etc. So yeah, we have a broad range of offerings for this market. What we'll concentrate on today is really the cell monitors and the ISO SPI transceiver and the roadmap going forward. So just typically sorts of applications that get put into energy storage as a space, we kind of segment these into kind of 5 areas, but I'm really going to talk about the residential, CCI, and utility today as a focus area. So let's just start off with the residential, and just to kind of give you an idea where these components are used. So this is a fairly typical kind of block diagram that you'd see of a residential system. So you'll normally have some form of AC fault protection. You will normally have an inverter in the system, whether a separate box or an integrated inverter. And then you'll have a localized power supply, isolated, which is generated, some battery protection, and then a number of cell monitors, depending on the type of stack that you're doing in your individual application. Some kind of isolation into a microcontroller, and then normally some type of isolated communications, be it CAN or isolated 485. So the particular area we're going to focus on today is really our cell monitors and the associated magnetics for the isolated SPI. This I'll just hand over to Martin to discuss.
Yeah, thanks, Nigel, and hello, everyone. So in the last slide, you have seen a nice overview about electric energy storage systems from Nigel. And of course, this is a complex system. Let me give you a bit another overview about battery management system, as you can see here in the left picture. So here you can see how actually a battery is looking like. And on this battery connected, there is this battery management system, as you can see in red. Yeah. And when we zoom into this battery management system, then we see on the right side 3 different kind of boards. These boards are the battery cell monitors. Yeah. And these battery cell monitors, they are connected to the battery cells. And you can see these battery symbols, and every battery symbol stands for a pack of battery cells. So in this case, it could be 10 to, let's say, 14 different cells, and they are connected over wire to these cell monitors. And on this, these boards, they are connected via daisy chain, and they go to a controller board. And on these battery cell monitors, there you can see the analog devices chips, and you can see also the BMS transformers. Nigel, can you please go to the next slide? So here, this is one of the boards, yeah. Like I said, on the left-hand side, you see the symbols stands for the different battery cells, yeah, which are connected to the board. And then you have in blue, like the ADI blue, yeah, the chips, and in red, there you can see 2 components. Each one, the bigger one, this is the transformer, the isolation, and the smaller one, this is a camera mode choke. This is against EMI. Yeah. And with these short words, I already give over again to Nigel.
Okay, thank you, man. So I just want to kind of give you a brief overview of our different cell monitors and areas we tend to see them being used. So, on the left is our released product. These are all out today. If you Google any of these part numbers, you will be able to see them. Martin was just showing you an example of the LTC 6811 part there. And we have higher channel CAN parts, the 1818. And then also for more CCI and utilities and larger systems. We'll also introduce later the 6815 family and the 6830 family of parts, which is kind of the parts that we tend to see used in those sort of systems. Also, as you could have seen from the previous diagram, there's a controller unit to this where you'll need to generate the ISO-SPI so you can daisy chain these devices to talk to each other. So we have a series of isolated transceivers as well, called the LTC 6820, and we've got the ADBMS 6821 and 22, which we'll talk about in a minute. Just to give you kind of a brief look ahead as well, we're also working on some 14-channel devices that we'll be releasing soon for with and without current sense amplifiers, and some SPI to UART converters as well, which work over an isolation transformer in the same way. So we'll just introduce the different parts as an area. So starting off here, we're starting with the LTC 6811 that's been available for a little while. So this is an example of a 12-cell battery stack monitor. It's a multiplexed architecture. Essentially, you can read the voltage on each of the cells, and then you can cascade it up through the ISO-SPI to get the different voltages up and down the stack. So, it also lets you monitor a couple of external temperature sensing points as well for thermal sensing for the batteries. So this part's available, has been out there for a while. If you want to move up to kind of 18 cells sort of parts using the similar sort of architecture, we have the ADBMS 1818 product, which is available, 3 millivolts total noise, also includes 200 milliamp passive cell balancing capability, and some more GPIOs, which can also be used for analog inputs for temperature sensor monitoring or alert inputs using ISO-SPI. Just coming soon on the 1754, 1755, we're coming up with a new family of 14-cell devices, which are capable of balancing up to 300 milliamps. We can daisy chain up to kind of 32 devices to do kind of higher stacks, etc. And as you can see here, this isolation is where you would see the Würth products being used this way. And the 1752 is from the same family, but what we include here is also the integrated current sense amplifier on the part. So these can be essentially used to monitor the current down through the stack at the same time in that architecture. Eventually, these need to be read into a micro somewhere to assemble all these data. So you'll need a bridge chip normally to take in from the isolated bus and transfer that into the micro. So that part will be the ADS 1751. So with that, I'll just hand over the presentation here to Martin, and I'll let you share your screen.
Nigel, I try to share.
Yeah.
So this should be better. No?
Yeah, looks good, Martin. Yeah.
Looks good. All right, good. So after Nigel gave you an overview about battery systems and of course also the necessary ICs, then I will go a bit into detail about the other types of products. So this is the BMS transformers. Again, you can see on the left-hand side, this is the picture that I showed you before with the battery cells here and the battery cell monitors and the controller boards. And here are the battery management transformers. And when you look on the right side, then you see application information also from analog devices, from the data sheets. There you can see where the transformers are inside. Yeah? They are exactly also between those boards. Yeah? You can see them here, and you can see them here, and you can see them, of course, here. Yeah? There are the elements. You can also see they are terminated in the middle with the middle pin with 10 nanofarad capacitors to the ground. So for these battery management systems, we have different transformer types that we have in our product program. First of all, this is a very small type, yeah, with 6 pins. This has is one transformer and one camo choke. Yeah, this is for example, if you use this in a daisy chain, you need 2 of them, or you have them at the end at a controller board. Yeah, we have them in 2 different versions. One version is with middle pins, one is without. This is depending on how you do your application. In the analog devices datasheet, you can find both ways how to connect them to ground. We recommend that you directly take this one with the with middle pins here. They are also there's no price difference between the ones with middle pins and without. We see no disadvantage. In opposite, we see an advantage for EMI if you take this with the middle pins here. Yeah? We of course also have smaller or less height versions. Yeah, if you have a stacked battery system and you have boards very close together, those have a height of 3.45 millimeters. We have also some with 2 camo chokes and 2 transformers. This is for daisy chaining, so you only need one package, one article here, and then you can do your daisy chaining, or if you need this in low profile, we also have this. So the features of those products are, of course, we need a high working voltage. 1000 volt is really, really high for working voltage, and later on you see 1.5 kV. So this was very not hard for us to make, but it was a big challenge for us. 1000 volt of working voltage. Normally, if you think on LAN transformers, and I come from the LAN transformer business, we have working voltages of maximum 250 volts. So this is 4 times higher, and therefore we had to very carefully to make our tests with that. Yeah, the test voltage, this is 4 kV or 4.3 kV. This is easily done, but 1000 volt working voltage, this is not easy to reach. Yeah, for that we do this. We do this with all products nowadays, that we do ACQ 200. With those kind of products, it was even harder, especially with this working voltage of 1000 volt. But we did the ACQ 200, and we could only reach this, of course, with a good wire. Yeah, so we have a manufacturer here, which is German based, and he's quite famous for good wire, and therefore, we took this one that we could be sure that the results are good. Yeah. And one special thing from our design is how we wire the wire. Normally, when we think on creepage and clearance distances, especially creepage, then we need to consider that the cores are out of manganese zinc. And manganese zinc is a leading material, and therefore, to reach the creepage distance, we had to use a trick, and this is what you can see on the right-hand side. So we have a special form of the cover, and therefore we can move the wire around and increase the creepage distance. You can see this on the next slide here, where we see those different designs, competitors in our design, and on the right side you can see some pictures where we can see how this is made, with a different housing type, so that the wire has a longer length, really to guarantee the creepage distance. The BMS transformers have some different parameters compared to parameters that you maybe know from things like LAN transformers. Yeah, both are transformers, both have camo chokes, but some parameters may may be strange for you guys when you want to implement BMS, and therefore I was thinking that it could be useful to talk about this a little bit. First of all, you see inductance values, and when you look normally at land transformers, then you have a minimum inductance value, but not a maximum inductance value. What is this about? The reason for this is seen at the temperature range here. We have minus 40 degrees to plus 125 degrees. And every core is out of a ferrite material, which has a permeability. And this permeability is depending on the temperature. Low temperature means low permeability, and this means also low inductance. And therefore, at low temperature, we have 150 microhenry, and at high temperature, we have up to 450 microhenry. I was said that analog devices, PHY chips, analog devices ICs can work up to 60 microhenry. Yeah, so even if in the coldest temperature, everything should work properly. But these are the requirements of the datasheet. Also interesting is what we have here. We have functional isolation only. What does this mean? Does this mean we have a less quality wire? Is this so? No, it's not. When we look at this information also combined with FIW6, then here's the explanation on this side here. This is how we choose the wire for this high isolation. There are norms. In this case, this is the IC 62368-1. And if you want to choose a wire, then there are tables. In this case, it's table G5. And yeah, we have different wires that we can take. In this case, we took 2 wires, FIW6. And when you follow the diameter and the grade of the wire, then we come to 2,800 volt of isolation. As we have 2 wires, we have 4,600 volt of isolation normally. Yeah, and with this functional isolation thing that we say we have functional isolation only, it could be that it's also working for basic isolation. Yeah, according to the IC 62368-1. Reinforced isolation, this is not possible. It's not that the wire could not hold a high isolation or the voltage. It's the rule or the IC 62368-1 says that between the primary and the secondary side, we have to add an additional isolation, like a tape or so. Yeah, and but as the wires are drilled together, we cannot add a tape, and therefore we cannot say it's reinforced isolation. So functional is possible, maybe also basic isolation. This is what will come maybe next, but we will see. Yeah, and these were now the details for the BMS transformers for 1000 volt, and now Nigel will explain you the BMS systems for higher voltages, and this is up to 1500 volt.
Okay, thank you very much. Let me just share again. Okay. So we've talked so far about residential systems typically, you know, and the voltages there tend to be relatively low voltages. As you move up towards grid scale and utility sort of applications, there's kind of a trend in the market because we're shipping very high currents around the place in this application to try and maximize the voltage in the stacks. Now, traditionally, they used to be, 400 to 800 volts, and that's moving at the higher end fairly strongly up to 1500 volts, which is kind of the maximum voltage you can get to under the low voltage directive. So we have a lot of customers moving up to 1500 volts. So what you're finding is a lot of people are stacking battery modules up to higher voltages, and also the battery modules themselves, in some cases, are also going up to high voltages in individual battery modules. So typically in a grid system, you'll see a number of battery racks, which will be attached with ISO-SPI, and a master control module, which will handle a lot of the communications, look at the current into the pack, into the rack, etc. And they'll work to balance the different racks between the systems. In some of the lower voltage systems, you had separate DC to DCs. In some of the newer systems that are coming through, that you're actually doing direct connections from the battery modules into the inverter chargers from a system perspective. So we tend to find that we, use ISO-SPI to communicate down to the battery modules. Depending on the configuration of the battery module and battery rack, sometimes you'll also want to do isolated CAN bus or Modbus on those if they're a switchover control module, battery module. Or sometimes that's just done up at the master control module space. So there's different architectures that people do. But just to kind of give you an idea of what goes into a grid system. So what I'm just going to cover here as a block diagram is the master control module at the top of the rack. So typically we would have, this is kind of 1500 volts. You'd have your contactor. You'd normally have your pack monitor and you'd measure the amount of current that is going into the battery modules. And then these are all the stacked battery modules that you'll see down the left-hand side. And then, the communication can be by ISO-SPI if it's a more vertically integrated system, or it can be by CAN or 485 if you want to use the more industry standards for the inverters, etc., that are available. So typically this is the sort of diagram that we see on the master controller. So usually when we talk about the ISO-SPI transceivers, they sit in on this rack, on this master controller rack. If I just go back, they would typically sit here. And then if I just give it a few minutes to stabilize, if we look at a battery module and rack where you would have one cell monitor or multiple cell monitors, depending on how many cells that your architecture is calling for you to have in the pack. You would normally have the different cell monitors in the pack, some kind of UV-OV protection, some kind of a thermal cutout for safety, and you would normally have a daisy-chained ISO-SPI that would come into the cell monitor unit, back out of the cell monitor unit, and then multiple racks can then communicate via ISO-SPI. So this is kind of a typical block diagram that we would see in grid and utility. So just coming back to our roadmap, which I presented earlier, what I'm just going to cover here quickly is a bit more about cell monitors and our isolated transceivers that we tend to see used in that area. So starting at the smaller cell counts as well, the 6815 and 6817 have been in here. These are, again, the first generation kind of multiplexed architecture. These are also 300 milliamps passive, and you can use multiple ones of these up to the system. So we can tolerate up to 85 volts if you're doing, say, a 48 volt nominal stack upwards, or a low voltage stack upwards, then we can use 6815, 17 for that area. One of the key differences that analog devices does on BMSs, and it kind of becomes important for your overall minimum power levels that you can provide from grid, is a lifetime total measurement error. So we specify on the data sheet a 15-year life cycle total measurement error. in typical operating conditions for energy storage, which tend to be slightly lower temperature ranges, we can also extrapolate that out to 20 years, and we have some kind of proof that we can show you those sort of total measurement errors on that. So if you want to get in contact with that, I can send you some information on that. Just to cover the BMS 6830, which is kind of our newest generation. Again, we specify 2 millivolts total measurement error over temperature and lifetime. So that's actually that's what we've tested, not just for the ICs, but with the ICs embedded on a board over life cycle and test. And why this matters is because if you can guarantee a certain measurement accuracy, ultimately it lets you use less cells in a big energy storage system. So it saves you the number of cells to supply the minimum service contracts that you've got to be able to comply with for utility type applications. One of the key differences between the 6830, which is our latest generation of parts, and the previous generations that I've talked about in here, is that we've got a true dual redundancy for sigma deltas. So each channel that we're looking at each cell over actually can measure the voltages twice for the primary and redundant channels. This lets you do get a redundant measurement for UV/OV detection and stuff. So this can help an awful lot with the amount of components that are needed to do a SIL capable design in the application. Just in terms of GPIOs, again, these can be used as analog inputs. So again, they can be used for doing a lot of thermistor monitoring for cell temperatures on a single chip. So just to cover the ISO-SPI transceivers, so the LTC 6820 was our first generation of ISO-SPI, which is 2 megabits per second. So typically the master control module will be transmitting data through down to each of the battery management system ICs further down. So this is good for 2 megabits per second and for lower voltage stacks. As you're starting to move to higher voltage stacks and you're still trying to maintain a read rate of kind of 50 milliseconds for voltage up and down the stacks, then sometimes you'll need to move up to slightly higher data rates or dual data rate systems. So with the 6820 and 22, we can actually read half of the bus at each time, so we can kind of double the data rate, which can come in handy for these higher voltage stacks. So this is kind of the newer generation of the ISO-SPI. So 6821 is the single, 6822 is the dual version of that. So with that, I'll hand it back to Martin.
Thanks, Nigel. So can you stop sharing?
Yeah.
Perfect. So okay, I need to change this. So now it should work. Perfect. Yeah. Now we have heard about the ICs for ESS grid scale, and of course the transformers should not be missed here. Here we have the big guys, yeah, of the transformers. We can see here we have a working voltage of 1.5 kilovolt. This is very, very much, yeah. And also we have a high pot primary to secondary side of 6 kV, and this should be hold for 60 seconds, yeah. So this is special on those parts. Here we cannot make this trick with this housing that we enlarge the creepage and clearance distances. Here we need to have larger diameters or larger distances between primary and secondary sites so that we can hold the clearance distance and creepage distance, so that there is no energy going over the customer PCB. Yeah. We have two different kinds of products. Sorry, first one is this here. This has 2 channels. Yeah, this is product 1. We also have this the same thing without the middle pins. Like I explained before, for those customers who want to make another termination. And then we have a part which has 1 transformer and 1 camo choke only, as you need 2 of them for daisy chaining then. Yeah. Special on those things in the data sheet is what I show you now. Yeah. Again, here this 150 to 450 microhenry. As I explained before, this is depending on the temperature. Yeah. And then we have the high port 66 kilovolt. And what we are doing to test this is, there's a HiPod testing equipment that we have, where we measure primary versus secondary side also after reliability testing. Yeah, and the parts need to withstand this. They withstand this because we use another wire. Yeah, the parts before with 1000 volt working voltage, they have FIW wire. This is fully isolated wire. This is a wire which is dipped many times into plastic for the isolation, and here we use TIW wire. TIW wire is triple isolated wire, and this means we have really like 3 wire isolations over the copper, and we use this wire on the primary side and on the secondary side. So we have 6 isolations, between 2 copper wires, and therefore we can hold this 1.5 kV of working voltage. But of course, it's not only the wire, we also need to test this. And how we test this? We test this with partial discharge testings. Yeah. What is a partial discharge testing? Partial discharge is if you apply a voltage from primary to secondary side. In this case, it's this 1.5 kV. And a certain amount of electrons should not go from primary to secondary side. If this would happen, the insulation can be damaged over the time. Yeah, and there's a norm for this. And what we're doing basically is that we go a ramp up to more than 1,500 volt, 25% more than 1,500 volt. Hold this for a time and then go down to 1,500 volt. Hold this also for some time. I think it's 10 seconds or so. And if the parts, if the partial discharges are under 10 picocoulomb, under this line, then the parts have passed the test. Yeah. Here there's a small mistake. We made the limit as 5 picocoulombs, and normally it should be 10 picocoulombs. This is the partial discharge test then. Yeah. Reinforced isolation. Here we have reinforced insulation. As I told you, this is because of the wire that we this time we use this triple isolated wire. Yeah. Here you also can see, maybe also interesting for you, how we define clearance and creepage distances in our data sheet. And here's some short information for you guys. If we say we have a reinforced insulation, and then we define a pollution degree of 2, yeah, then we go over to the insulation test voltage that we can do. Yeah, in our case is 6 kV, and then in the table in the ISC 62368-1, there we find it's 8 millimeter minimum of clearance distance. Yeah, for real, this clearance distance is longer, is more, but we rate a minimum creepage clearance distance in the data sheet. Analog to this is the creepage distance. Also here, we define the pollution degree and the material group, and the working voltage. In our case, is 1,500 volt. Question to some of you guys, maybe why not more? Can we go more to 2,000 volt? Theoretically, yes, but this would would not be low voltage anymore. Yeah, so therefore we have other norms. Yeah, the norms that where we working with, the limit here is 1500 volt. Anyways, if we follow this, then we have the 8 millimeter. But when we look at some additional information for reinforced insulation, we need to double the value of basic insulation, and therefore we come to 60 millimeter of minimum creepage distance. Yeah. Now you know how how we define our values in the data sheet. Yeah. And with this, I'm finished. Thank you very much for listening. And if you have questions, then please let me know. You also can send us emails, nigel.brook@analog.com or martin.leinzeder@we-online.de. Many thanks.
Thanks, Martin, and thanks, Nigel. Some enlightening stuff in there, I think, and well, some scary voltage levels in there too from a battery pack. So it's interesting to see the trend of higher and higher voltages. We've got a few questions come in, and let me just find a couple of those in the Q&A. And I've answered a couple as we've been going. One of them was around things like a difference between the AEC automotive standards, and there are lots of reference documents out there for anybody interested in that. Couple of questions for you, Nigel, I think, around the AFEs. And one of them is on measurement error, which is quite an interesting one, and it might be something you need to take offline. But why in the new generation of AFEs the ADC has a higher total measurement error compared to the current generation? And the example given was 3.5 millivolts instead of 2.
Yeah, so we see two different trends. So it really depends on the end market and what's pushing it. So we could almost talk about this. It's really a market-driven specification in two different directions. So if you're selling more to the grid utility side of the market, right, you're talking about lots and lots of batteries that are sitting in a big shipping container type of box. So there's a huge value in terms of the total error and the number of batteries you can save in that sort of system, right? So getting the tightest accuracy is why we tend to see parts like the 6850 and the 6830 used for the grid utility sort of applications, because the actual system savings is really in how many batteries you need to achieve your minimum service level. However, that costs, right? So there's a genuine cost associated with that from a technology perspective in terms of the testing, the trimming, getting everything right at that side of the market. So we also see in more consumer and residential things where the cost is getting driven lower and lower. So really what we're actually doing is reducing the amount of trimming and testing we're doing on some of our cores to save cost for some of those applications in the newer applications. So that's really where the difference comes. So it's market driven. Yes.
Very much engineering for the like you say, the end market application then.
Yeah.
Okay, that's totally understandable. Another perhaps a less detailed question was around when will the next or new gen AFEs be available in SOP package?
So the new generation AFEs, we're expecting will release in kind of December sort of time frame, just to give you an idea on that for start of production. So that's so basically it'll be kind of December. So they're actually going to be QFN based.
Oh,
products.
sorry.
Yeah,
Let me just start of production.
Production probably. Yeah.
Sorry, not. Well, I've mistook that for being package. Thanks for the clarification. There's no name against it, but thanks for the clarification. So and you've answered it, I think, which is basically tail end of Q4, early Q1, I would say.
Exactly.
A couple of others. compliments on the presentation from some attendees already, so that's nice. One question I had in mind, I think, listening to what is I guess, a complex and also a safety critical, part of any battery management application or any battery powered application is, do you have some reference designs for a BMS? And that includes firmware references, so a complete kind of reference package.
Yeah, so what a lot of our so if you look at a lot of our BMS chips, for example, we will tend to do two versions of them. So we'll tend to do they're the same design, same silicon, right? But we will do a functionally safe product, which normally comes from the automotive industry, ASIL, and then transferred to SIL. And we have functionally safe product manuals on those that we provide under NDA. So if somebody wants to get in touch with us, sign an NDA, which is just a fairly standard form, we can provide safety manuals on most of our BMS chips.
Okay. I guess what the question coming from a gentleman called Michael Knoll is more around, is there a hardware board? Is there firmware that goes with it that you can, an evaluation board?
Absolutely, yes. So we get an evaluation system together at the moment, which essentially becomes the BMS boards, the ISO-SPI boards, a microcontroller board that links into a PC, and then we can have software that essentially runs on a PC that will give you a demonstration of what all the stack is. We also have some Python wrappers and stuff, so people can kind of run their own systems. So we have a system to get people up and started. I mean, eventually what tends to happen is people will need to write their own firmware to get the throughput rates they want in these systems.
Right.
But we have starting points to get everybody started.
Very good. Get people off the blank page. Exactly. Yeah. So that was reference designs. And I think here, our OVC2 class 8 kV also in the roadmap, which I think is Martin, I guess.
OVC2 over voltage category 2 class 8 kV, so 8 kV of isolation. I'm thinking on how this is meant. If the question is 8 kV for 1 minute, then I would say at the moment, no, it's not on our roadmap, but it could be that 8 kV is meant that it's some kind of a pulse testing, which is required. We have questions from different customers by now, and they mentioned some kind of pulse testing for 8 kV, and this could be possible also with the products we have right now. So it could be a matter of testing. But I would recommend the person who wrote this email that they go into contact with us over
LMR. So Rain, I think it's a direct question to the guys there, I think. And also we will, at the end of the presentation, in the days following the presentation, we will give written answers to these questions too. So of course, if you want to dig in further, then feel free to accept Martin's invitation to contact them by email. And I think we have time for one more, which is from Ricardo, and he's asking, one concern that arises with communications is what will be the behavior of the cell management when communications breaks down. When communications breaks down. Are there safety timeouts which will protect the cells from being depleted?
Yeah, so there's two ways I think of looking at that when you get into detail and things. So firstly, this is actually one of the key reasons why we're doing the ADBMS 6822, which is the dual channel version. What that actually lets you do is, if there is a break in the communications, is rather than having to go cycle around all of the communications in one direction, you can actually cycle back both ways and find out where the break is. Right. So it actually helps you diagnose where those sort of breaks are. So there's a there's a number of different ways to look at that. So a traditional kind of way with some of the first generation points is they'll tend to also be a separate hardware redundancy that if something stops, then something goes over voltage or under voltage, it will switch out, right? This was one protection you would tend to have in a safety critical system. In the 6830, one of the ways that we protect that now is we kind of also have a everything's okay signal, which transmits every so often. So if you don't get that within a certain period of time, you can shut your system down for safety.
Very good. Thanks, Nigel. So that's really all we have time for. I think that's been an excellent both presentation and also a really good Q&A session at the end there. As I mentioned, then questions will be answered in writing and be made available to all participants. And of course, should you wish to watch the webinar again or share it with others, we'll also be sharing the link for the on-demand version. There have been several requests for to make the slides available, but I think certainly the on-demand is available. I'm not entirely sure if we share the the raw slides or a PDF version of the slides. So once again, Nigel, Martin, thanks very much for your collaboration and an excellent webinar here. For all those participating, there is a short survey coming up, and we would be very grateful if you could provide some feedback and help us improve future webinars. But for now, and until the next time, thank you very much. Thanks, Nigel. Thanks, Martin, and see you again soon.
Thank you also very
Bye.
much.
Thank you,
Bye.
everyone.
Thanks. Bye.
Bye.